Hello, everyone. Morning, or good afternoon, good evening, depending on when you are listening to this video lecture. Let me welcome you once again. This is our first recorded video for our lecture that we used to have last week. But unfortunately, because of technical challenges, we were not able to finish the lecture. The main challenge I've been having lately is the internet connectivity. Sometimes the internet makes the connection impossible. That's why on my end it appears to be very good, but when you're listening to me, you might hear my voice is breaking. But at least with this kind of recording, I want to believe that my voice will be clear. You'll be able to follow everything from the beginning to the end. So welcome once again. This is lecture number 3 on Maxwell's equations. It's a continuation of the previous lecture, which was purely on introductions to Maxwell's equations. So welcome once again. All right, so sorry for that. I was trying to navigate to the next slide. So we are basically going to look at 3 areas. That is, first we shall review the Maxwell's equations that was introduced in the previous lecture. Then we will look at what we call the constitutive parameters. And then finally, we shall look at questions that you have to use the Maxwell's equations to solve. And this is actually the main part of this lecture, how to apply the Maxwell's equations. So first, let us review what we had already discussed last week. The first Maxwell's equation takes the form of what we call the Faradays Law. Faraday's law, as we all know, even without looking at the equations, in your electricity and magnetism 1 or 2, you must have discussed what we call the electromagnetic induction. And in that discussion, you must have talked about how a conductor interacts with the magnetic fields. And because of that interaction, you have induced current produced in a conductor. And of course, the induced current gives rise to an EMF. So basically, that is what Faraday's law is all about. Then you must have also come across different equations. And one of the equations is the definition of electric field intensity, which is basically force per unit charge, or alternatively, it is voltage divided by displacement. Now, with that being said, if you look at this equation here, if you can see my cursor, you have electric field intensity being multiplied by a displacement or a path. So this product, the dot product of electric field intensity and the displacement gives you voltage, because voltage, definition of volts or potential difference is that it is, electric field intensity is potential difference over displacement. So this first term you see here is voltage. Now, if you look at the differential form of Maxwell's equation, you have the rate of change of magnetic field or magnetic flux with respect to time. So the Faraday's law basically is defined as the rate of change of magnetic flux is directly proportional to the EMF induced. And that is what is contained. So you have a product of E and displacement giving you voltage, And then on the right-hand side gives you now the rate of change of magnetic flux with time. If you look at the differential form on the right, you can clearly see that it is the rate of change of magnetic flux B, and I mean with respect to time. So then if you read this, we first of all say that the physical quantities that appear in Maxwell's equations are the electric field intensity E, the magnetic field intensity B, the electric flux density D, the magnetic field intensity H, and the electric charge density Rho. We have basically come across E, B, and Rho. We have not looked at equations with D and H. So when we come to that part of constitutive parameters, we are going to link the electric flux density D and electric field intensity E. Then we shall also link magnetic field intensity H and the magnetic flux, which is B. So when we get to the constitutive parameters, just remember that. And so the Faraday's law I've already explained. It's about how induced current comes about due to interaction of magnetic field with a conductor. We basically say it is the rate of change of magnetic flux is directly proportional to the EMF induced. So that is what is contained in the Faraday's law. And then those quantities that we have looked at, like for example, the displacement is basically the circumference of this figure here, which is dl. All right. So that dl is a closed path. C, labeled C, and then it covers a protruding surface. It covers a protruding surface, SC, and the normal vector on that surface is what we have as ds. So if I just go back to those equations just a bit, you see dl, this displacement that I've mentioned, is actually a closed path. Yeah, is like the circumference of a closed path, and then ds, this one here, is the normal vector on the surface, is a normal vector on a closed surface. All right. So this SC simply shows that surface. All right. Here we should have had C for that closed loop for DL. So if you need to see those parameters, you look at this figure here. Then the next equation of the next Maxwell's equation is what we refer to as the Gauss law. All right. So Gauss law is a mathematical expression of the experimental fact that electric charges attract or repel one another with a force inversely proportional to the square of the distance between them. So reading that statement alone rings a bell, because that is what we started in our very first lecture called the Coulomb's law. That when two charged particles are brought together, we can either have repulsion or we can have attraction, and that magnitude of force between the charges is inversely proportional to the square of the distance between them. So the Gauss law is what is contained in the Maxwell's equation number 2, and it is expressed in this form. So it basically expresses the Coulomb's law. All right. So the Gauss law basically expresses the Coulomb's law, and you can see we have the integral form, which we have the magnetic flux intensity D, electric flux intensity D, with a dot product of the normal vector to the surface ds, all right? Then is equal to the negative of integral of the charge density rho and the volume of a closed figure, all right? The volume of a closed figure, which is given by dV. Then on the differential form, we simply have the divergence of that electric flux density D, all right? So when I say divergence, I basically mean it is the del dotted with a vector quantity. That is what we call the divergence. So we have the del operator dotted with the electric flux density D, and that gives you the charge density, right? That gives you the charge density. So this one, there is a way in which you can express it so that you see now the Coulomb's law comes out of it very clearly. Because Coulomb's law is basically force is equal to a constant multiplied by the charge squared, then divided by r squared. That can be seen here because this this del operator is a differential with respect to displacement, right? So the del operator is a differential operator with respect to displacement. That is, you can differentiate it, you can differentiate a vector quantity with respect to x, with respect to y, with respect to z. So Gauss law is expresses the Coulomb's law. Then the third equation is what we call the Amperes law. All right, Amperes law, which states that the line integral of the magnetic field over any closed loop must equal the total current enclosed by that loop or contour. That should be very clear that the line integral, you know, when you integrate a quantity over a line, we call it a line integral. So when you integrate the line integral of magnetic field over any closed loop, because a closed loop is basically a displacement. So you're talking about, you're integrating, it could be a circumference, it could be any crooked path, but it is closed. The beginning and the end, you start at the same point, you start at a point and then you end at the same point. That's what we call a closed loop. So the line integral of magnetic field over any closed loop must equal the total current enclosed by that contour. And that is shown here, that you have the magnetic field density H with the dot product of displacement of that closed loop being equal to the integral of the, hold on, let me go back. It being equal to the integral of current density J with the normal vector on the surface ds plus the rate of change of electric field density d with time, then dotted with ds. Basically, what I'm trying to say is the Amperes law is just an integral of the magnetic field density dotted with a closed loop, and then on the right hand side you have two components. These two components, the first component here is basically the Ohm's law. All right, the first term here is basically the Ohm's law. You might not see it clearly, but there's a way in which mathematically you can show that J dotted with the normal vector S gives you the Ohm's law, and then you have a term which is the electric field density differentiated with respect to time and dotted with the normal surface vector. That is the integral form. But if you simply take it on the differential form, you have the curl, okay, the negative curl of electric field density D, all right, being equal to the charge density plus the rate of change of electric density with time. So this is the Amperes law. I would encourage you to basically just know how to write it. Then these meanings that I'm trying to explain will come out clearly once you know how to express it. And then the Ohm's law that I'm trying to show you, you can actually substitute what J is from the definition, and then it will now come out into what we know is equals to V is equals to IR. That is I, which is the current multiplied by the resistance. So we're saying where the loop C encloses the surface as C, shown in earlier figure 1, the Maxwell's third equation expresses the fact that time-varying electric fields produce magnetic field. I think that last sentence, if you remember, there was an experiment done by somebody called Oersted, O-E-R-S-T-E-D. In this experiment, there was a discovery that anytime current flows in a conductor, there exists some magnetic fields around the conductor. And that is what we actually call the magnetic effect of electric current. That current does not just flow because of flow of charges, but current gives back to magnetic field. So you can actually see that you have the magnetic field, and then on the right we are talking about electric charge. All right. So it's basically the Oersted's experiment that electric current gives back to magnetic field around a conductor. So there are different ways in which you can explain the Amperes law, provided you are basically containing yourself within the parameters of the equation. Then the fourth law is actually the most common and the most simple one to understand. Basically, if you simply look at the differential form, which is on the right here, if you look at the differential form of the fourth law, you can see that the divergence of a magnetic field intensity is 0. In simple language, it simply means you cannot have a north pole existing without a south pole. You cannot have a south pole existing without a north pole. In technical terms, we say there are no magnetic monopoles. All right? We don't have what we call the magnetic monopoles. You cannot have a north pole standing on its own. You cannot have a south pole standing on its own. But when it comes to electric charges, it is possible to have a positive charge alone, a negative charge alone. But for a magnetic field, you cannot have magnetic monopoles. And this is what is contained here. So this equation can be derived from the Biot-Savart law, and so it is not completely independent. All right, like I've just said, this is the most easy equation to explain, because remember, one of the common questions that come into under this Maxwell's equation is to explain the Maxwell's equation from equation number 1 to equation number 4. What each of those equations mean under their expression. That one you must never forget. Okay? So then we had already mentioned something called the constitutive parameters. The constitutive parameters relate the electric field intensity with electric field density. We have the magnetic field density, magnetic field intensity, or the magnetic flux. So you have this quantity D, which is being equated to the permittivity of the material multiplied by the electric field intensity. For the magnetic field, you have the magnetic flux intensity B being equal to permeability of the material multiplied by magnetic field intensity. So these two are what we call the constitutive parameters. The reason why you need to understand these constitutive parameters, because sometimes when you read different books, you will find Maxwell's equation written in terms of D. Some equations will be written in terms of E, but it is basically the same thing. All right. The connection between D and E must have this permittivity E. Again, some equations will be having B, some will be having H. It is the same equation, only that They are connected by the permeability of the material mu. If these expressions are, if the connection is being done in free space, then the material becomes, for example, the permittivity will be the permittivity of free space. The permeability will be permeability of free space, and that will be epsilon naught mu naught. The current density J is in general given by J is equals to J source plus JC, where J source represents the source current from which magnetic fields originate, and JC is the conductivity multiplied by the electric field intensity. Represent the conduction current which flows in conducting medium, and where the conductivity is not equal to 0, where the electric field is present. I think this expression of J, sometimes what is being said here is that you can have a Maxwell's equation expressed with only two terms. For example, the Amperes law. The Amperes law can have two terms on the right. It can have only one term on the right. So that depends on whether J has J source plus JC, or it is basically J is equals to JC. It depends on whether the conductivity is 0 or not. If this conductivity is 0, then you will have J being equal to only J source. But if the conductivity, this one written with the symbol of sigma, if the conductivity of the material is not 0, then J will have two terms. Let me just go back slightly to the Amperes law so that you can see what we are saying. You see, like in this case, you have the Amperes law being expressed with two terms on the right. If you look at, sometimes in other books, you might find only one term. So that depends on whether the conductivity of the material is 0 or the conductivity is not 0. So let's look at some questions. We have question number 1 here. Consider an electromagnetic traveling wave with electric and magnetic fields given by, what you can see there. So EX simply means the X components of the electric field intensity. That is written as EX. BY simply means the Y components of the magnetic field intensity. Now, remember this, that electric field is a vector quantity. And it being a vector quantity, then it must have the X component, the Y component, and the Z component. The magnetic field intensity is also a vector quantity. So it must have the X component, the Y component, and the Z component. So these are just extracts of the electric field intensity vector. So we have EX, which is not a vector, BY, which is not a vector, because these are components. Now, using Maxwell's equation, show that B naught can be written in terms of E naught. This is very interesting and very simple. So I would urge you to make sure you try to follow and understand, because it is this the understanding of this will build on the understanding of other complex questions. So what you need to reason here is that Maxwell's equations in free space can be used for both the electric field intensity E and magnetic field intensity B. They can be used to show that electric field intensity vector is perpendicular to the magnetic field intensity vector. Electric field intensity vector is perpendicular to the propagation constant K. Magnetic field intensity B is perpendicular to the propagation constant K. Before I continue, you need to recall that we have what we call the right hand rule that connects electric field intensity E magnetic field intensity B, and the propagation constant K. These three quantities form the corners of a cube, such that the three of them are always perpendicular. K is usually the direction in which the wave is traveling, which is called the propagation constant K. Okay, so figure that in your mind. If you can't, then maybe you can go to different books and see how E, B, and K are configured in a diagram. Okay, so these are the details of the calculation. From Maxwell's equation, we have this expression here, which we defined as the Faraday's law, that the magnetic flux density, the rate of change of magnetic flux, is directly proportional to the induced EMF. So on the left hand side, we have the cross product or the curl of the electric field intensity E, and this one you have to do it. Normally the cross product, you do it using the determinant method, so that you see exactly which vector is multiplied by which. So you use the determinant method to do that. And if you do that, you end up with this term that is shown on the right. All right, please take notes. I'm saying use the determinant method of cross product, and you will show this equation number 8. Okay, I may not be able to show it here, but I'm telling you so that you go and try. If you have a question, then you can raise it. So note, you have to use the determinant method of cross product to show this term number 8 here. If you do that, you keep this one aside, then you come to the right hand side. The right hand side is basically the time differential of the magnetic field intensity E. So you simply substitute B and you differentiate it with respect to time. All right, you simply do what the right hand side says, which means you differentiate the vector, the magnetic field vector, with respect to time. And when you do that, you get this term here on the right. So what does this mean? The first equation that you obtained using the determinant method, and the second one that you have obtained by differentiating B with respect to T, are equal, because the Faraday's law is what is shown on in the upper part here. So you do the left hand side separately, you get an expression. You do the right hand separately, you get an expression. And then you equate the two expressions. So when you equate the two expressions, you will get this term here. K E naught is equals to omega B naught, which you can rewrite as B naught is equals to K over omega E naught. So we have already shown what is required, that B naught can be expressed in terms of E naught. And it is good to note that the propagation constant K divided by the angular frequency omega is equals to K over omega is equals to 1 over the speed of light. That is a common term which you can always quote. So question number 1 is done. Question number 2. Use Maxwell's equations to find the magnetic field of an electromagnetic wave in vacuum, for which the electric field is given by what you have there. So this is a vector. It has two components. We have the X component and we have the J component. They have a common term, which is the sign of what is in the bracket there. So again, we need to inspect how to begin our solution. We have listed the 4 equations. That is from the divergence of E. Then we have gone to the divergence of B, then curl of E and curl of B, and we have shown that. So use Maxwell's equation to find the magnetic field. So we have been given an electric field, but we are being asked to get an electric field. So we can choose one of these equations to help us obtain B. All right, let's see what that is. Now, if you pick the Faraday's equation, the Faraday's equation is the equation we picked earlier, which is, let me just go back, which is equation number 3 for us here. Equation number 3 here means if you get the curl of E, that means you get the cross product of E with del, whatever you get will be equal to the partial derivative of magnetic field intensity with respect to time. So we pick number 3 here, and that will help us get B. So let's see what happens. So you get the cross product of E, and you get the middle term here. This middle term, you equate it to the partial derivative of the x component of magnetic field. And so, because you are interested in getting the magnetic field intensity, you then integrate the equation that you had obtained using the cross product. And if you do that, you simply do the integration and you obtain the term that you can see here. Okay, so this becomes the x component of the magnetic field intensity. All right, you do the same for y. You get the cross product of the E vector, and once you get the the cross product, you equate it to the partial derivative of the y component of the magnetic field with respect to time. You do the same thing, you integrate to get By, and once you get By, you get now the y component of the magnetic field intensity. You proceed and do for the third one, we started with x, you go to y, then you go to z, until you have the 3 components of the B vector. Then you will simply come to a solution and say the B vector is equals to Bx, that's for the x component, plus By for the y component, plus Bz for the z component. And you will have your complete B vector. Therefore, Bz is 0. Why is it 0? Because when you integrate this term with respect to t, you end up with 0. Okay, we are not, because we are not interested in the constant term. So when you combine the 3 components, like I've explained, you end up getting the final answer as indicated here. Okay, I wish these things could be done where I show you mathematically, but my explanations are good enough. If you simply follow and you take a pen and paper, you can prove some of these things that I'm talking about. Okay, this unit is heavily mathematical, so I would urge you that for a recorded video like this, after you listen, you can take a pen and paper and try to prove some of these things. Or you can even pause as you try, then forward, and so on and so forth. So then, we have a final question here. The electric field component of an electromagnetic wave in air used by an aircraft to communicate with the air traffic control tower can be represented by that form there. So we have an electric field component, which is given only for the y component. That's why you have the j there. Find the corresponding wave. Find the corresponding wave magnetic fields Hz and the constant B. Wow, this one is interesting. So in view of the sinusoidal nature of electric field signal, it is appropriate to work with phasors. Okay, there is if you remember your complex number, when you're doing complex numbers, you remember you can write a complex number in terms of x and y. You can write it in terms of cosine and sine. You can also write it in terms of the E. e raised to power j theta. So when you write it in that form, we call it the phasor form. That is called the phasor form. So an expression like this E is equal to J 0.02 cosine 7.5 times 10 power 8 T minus PZ is actually the trigonometric form of a complex number. And that can be expressed in phasor form as 0.02, which is the magnitude, E raised to power J BZ. B is the face of the vector and Z is the component. So then, if you again take the Faraday's law, you take the curl of E, because E is what you have. When you take the curl of E, you will get, this is basically the Faraday's law, but when you take the curl of E, you end up with an expression shown down here. They are not arranged properly. Sorry for that. But you take, basically you take the curl of E. Okay, that means you take the determinant, you use the determinant method where you normally take the I, J, K, then you have partial X, partial Y, partial Z, and you end up with an expression such as this. All right. So that expression, you equate it to the right-hand side, of the Faraday's law. And when you do that, you will have an opportunity now to express Hz. Because now Hz means you now integrate. You now integrate what you had obtained using the determinant method. So when you do the integration, you obtain this equation here. Right? This equation that you can look at my cursor. You obtain this expression, and you can simplify it by simply substituting the EY, that is the E component, in terms of the phasor, that is E power minus J BZ, where of course omega is 7.5 times 10 power 8, mu naught is the permeability of free space is given there, so that when you substitute the constants omega and mu naught, you will end up with the curl of H being equal to J plus partial D with respect to time, and obtain the following. I think I'm moving a little bit faster, but it's okay because you'll have the opportunity to go through this and try to do it yourself to see whether you're obtaining what is shown here. So if you do that substitution, you will end up with the electric field vector, which is a function of Z, as being equal to 1 over J omega E naught multiplied by the del operator, the cross product of del and H. Okay, that will be equal to J 1 over J omega E naught multiplied by the partial derivative of the magnetic field, the X component of magnetic field intensity with respect to Z, and then you substitute. Here, let me just, so that I don't just read what is here. These things that is being shown here, when you see like a term being repeated, and then there's something being introduced, it simply means there is a substitution that has taken place. For example, here, this is partial Hz over partial Z. There is a substitution for this, which is, yes, I think it is, let me see. Yeah, partial Hx was already obtained, and that was equivalent to 0.02 beta squared multiplied by E, which is a constant raised to power minus J BZ. So I apologize because I've put a lot of things together, which means you have to really like do it and prove that it is right. You know what? The problem is that when you are developing, when you're writing solution, which is equation, a lot of equation in nature, you end up putting a lot of steps together. But I would encourage you to just try to follow and try to do these things. So this expression for Ez must be the same as the electric phasor expression we started with. Thus, we must have E 0.02 beta squared over omega squared mu naught E naught is equals to 0.02. So there you can see the substitution that I have made, where we have the speed of light is equal to the square root of mu naught over E naught. The corresponding magnetic field is then given by Hz is minus I. So here, I think the substitution is for, you substitute beta. Where there was beta, you now put 2.5. And omega was, of course, 7.5 times 10 power 8, mu naught, and then you have the other parts remaining the same. So that when you multiply now the 0.02, 2.5, and 7.5 times 10 power 8, you end up with a single number, which is shown in equation number 16. So finally, the instantaneous magnetic field Hzt is equivalent to Hzt is equals to, that R is for the real component. The real component of Hz, blah, 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 Ej omega t should be equal to the real component, which is minus I 53.1. Yes, 53.1 Ej 2.5Z e power j omega t. Now, let me explain. You see, you must be asking yourself, why do we have the real parts of the complex number? It is because, let me go back here. You see, the question that we were given was cosine in nature. The complex numbers has real parts, has two parts, the real part and the imaginary part. For the trigonometric form of a complex number, the real part is usually the cosine form. So even without being told that this is the real part, it simply means that your final expression should also contain the real part. Okay, should also contain the real part of the final answer. So I think this is as far as we can go today. Let me hear feedback once you are able to follow, particularly this number 4. Yeah, whether you are able to follow the steps and prove some of the answers that are there. If you're not able to, then we can review it again, or maybe I can do it on a handwritten paper and maybe take a picture, if that will help. So I think that should mark the end of this lecture. Okay, so I will send you, yeah, I'll put the PDF in the Mkutano platform, so that you can download the PDF, but you can also have this video. So have a nice day or nice evening. Let's meet in our next lecture. Bye-bye.